balance has to realize the kilogram under vacuum. And that's because it has to do this with an extremely, extremely low uncertainty, this measurement. And when you do things in air, you introduce a lot of uncertainties, especially when you're using lasers for interferometers. The index of refraction of air changes based on the environmental conditions, and that can change your path length, which affects their velocity measurements. And so I don't know if you ever put this in context, but they're doing this measurement to about 20 parts per billion uncertainty, which is the equivalent of measuring the circumference of the Earth to better than a meter. So they're making really, really precise mass realizations down there. And so that's kind of why, that's the motivation why it happens in vacuum. Even if it adds all these challenges for us, it's the only way that we can do this realization and not drastically increase the uncertainty from the IPK. And so we actually do this vacuum to air transfer in two methods. The first one I just showed you, which was the magnetic suspension experiment. And the second one uses our vacuum balance, which is in the room next door. This is a Mettler-Toledo M1 mass comparator. So it's got a kilogram capacity and 0.1 micrograms resolution. And so the way that this experiment works is we put a traditional, say a platinum iridium mass standard in the vacuum chamber, which is 39 millimeters in diameter and 39 millimeters tall. And then we put in we call it a stack, a platinum iridium stack, which is 8 discs that are separated by 3 spacers on each level. And so this stack is exactly the same mass as the standard cylinder, but it's got a drastically increased surface area. And so what we do is we pump the chamber down and we measure both of those in vacuum relative to each other. And then we come back up to air and we measure them in air. We go back to vacuum, measure them in vacuum, go back to air, measure them in air. And through these cycles, we can build a model for what happens when you go from vacuum to air. And the result will give you something on the order of grams per centimeter squared. So we can say that for a given surface area, we expect to pull a mass out of vacuum and it increases by this amount of mass, given these back and forth models. And we call this our indirect method because at the end of the day, you're kind of fitting a line to a bunch of data. We like to call our magnetic suspension experiment our direct method because you're putting both these kilograms on the same balance. You're comparing them side by side through magnetic suspension. So that's not to say that this is a lesser method. This is actually what most of the world does because this magnetic suspension experiment took 20 years and multiple PhD physicists to develop and is not a trivial experiment to operate. And so the majority of the world does it this way, and we see our magnetic suspension experiment as a validation on this method. So if there are some sort of systematic uncertainties introduced by doing this vacuum to air system, we expect that our suspension experiment would show those systematics because it's a completely new set of physics that we're doing our comparison with. And so they're seen as complementary methods. We're not saying one's better than the other, although I'm a little partial to the suspension experiment. But this is where all the magic happens in terms of these absorption artifacts. And so Eric Bank, which is one of my colleagues, is currently doing measurements between a platinum iridium stack and a stainless steel stack, and then 2 platinum iridium and stainless steel masses. And this is important because these absorption corrections are very particular for the surface that you're dealing with and for the environmental conditions. So if I say that for a given platinum iridium mass, we expect X number of grams per centimeter squared when we go to air, that correction wouldn't hold for a stainless steel mass, just because the stainless steel surface is different than the platinum iridium surface. So you'd expect different bondings of the hydrocarbons, you'd expect different absorption characteristics or outgassing characteristics from the masses. And so to do this kind of correction, you need to do it for a particular surface and a particular set of conditions. And so right now we're doing platinum iridium masses in there, and we're doing stainless steel masses in there. Another reason that I'm not super fond of this method is I'm usually the one responsible for building the platinum stack on the turntable, which is the most nerve-wracking thing I do in my entire time here at NIST. You put one platinum disc on, and these tiny little tic-tac size spacers, and then you build the second disc, and you can get all the way up there, and you can realize that your spacers in your first level have shifted a little, and it's time to unbuild the whole thing and back on. And so usually when I know I have to do that, it's like an hour of meditation to get my heart steady enough to be able to handle these masses. Because I mean, these platinum iridium artifacts are invaluable. They're oftentimes more than 100 years old. They've got years and years of calibration history. So for me to bobble one of these little spacers or to bobble a disc would be pretty catastrophic. So I would prefer a system that doesn't rely on me playing like the scariest game of Jenga. But at this point, we're using this method in conjunction with the suspension method to do our vacuum to air transfer. And so that's all we'll be able to say here. You guys are welcome to come through if you want to peek in and see the balance. But this is a newer version of the balance we're going to show you in the next room too, so you can see it there as well.
You said it varies by surface.
Yes,
You were talking about material, but does it also vary by polish of an individual?
for sure,
lights?
even more
Okay.
so.
Right.
So since this is a function of surface area, if you have some root mean squared roughness of the surface,
Right.
and then you have one that's twice as rough, that you would see an enormous increase in mass just because of all the small facets. Because these processes that we're talking about are extremely small. We're not talking about droplets of water.
Right.
We're talking about like
Molecules.
atmospheric humidity. Sure,
Right.
sure. So these are incredibly small processes. And the interesting thing with these processes is there's actually two processes at work. There's physisorption and chemisorption. So chemisorption is generally an irreversible process that happens. So once something has been chemisorbed into a mass, it takes a lot for that to be released. Physisorption is more of a surface process that we see changes when we pump and when we bend and when we pump. So this is more of a cyclic reversible process. And so the data from these experiments is interesting. You actually see it, as you keep doing this, you see the masses continually increasing and then you see them leveling off. And that level off point is where we see the difference between our stack and our standard. And that's where we build our correction for absorption. And so that's a good question.
So you'd almost have to do each artifact you wanted to go through that process individually.
Yeah,
To be the most exact.
to be most exact, for sure.
Right.
At the level of uncertainty that it introduces, going class by class is generally, so if we know that an E1 class stainless steel mass behaves in a certain way, we feel pretty comfortable assigning that magnitude of correction to other E1 class masses, because we know that there are standards for surface roughness, and we know that there are standards for markings for labeling. And so that's what we do here, and then we're gonna head down the hall for our third tour stop, where we'll see one of our national standards, and our last portion of that tour